Hey guys, today we're going to talk about the addition rule. This will be for finding probabilities of A or B. Before we talk about the addition rule, we need to talk about the word mutually exclusive. Mutually means together. If you have a mutual friend with someone, you both are friends of that third person. And exclusive means that things are excluded. So together, mutually exclusive events means that one event excludes the other one from happening. So if one event occurs, the other one cannot possibly occur. Let's look at a couple of examples. For the first example, event A is randomly selecting a female worker. Event B is randomly selecting a worker with a college degree. So the question that we need to ask ourselves is, can a worker be both female and have a college degree? And the answer to that is yes, females have college degrees all the time. So if a female can have a college degree, then these two events are not mutually exclusive. One person could be both female and carry a college degree. For the second example, event A is to randomly select a person between 18 and 24 years old, and event B is to randomly select a person between 25 and 34 years old. Well, if I select someone that's between 18 and 24, that same person is not going to be 25 to 34. If you're in one of these groups, you cannot be in the other one. These groups mutually exclude each other. So those events are considered mutually exclusive. So now we can get to finding the OR probabilities. Here's the formula at the bottom of this page. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B. And this is not the multiplication rule A and B. This is an A and B happening at the same time. So we've said before that AND means multiply, or will mean add. Let's get to some examples. We have a problem about defective cartons, and we're given the probability of producing a carton with a puncture, the probability of producing one with a smashed corner, and the probability of producing both. First question is, are those events mutually exclusive? Well, can I have a carton that is both punctured and has a smashed corner? According to the probabilities they've given me, yes, I can. So they are not mutually exclusive because they can have both. So one carton can have both. Part B says if a quality inspector randomly selects a carton, find the probability that the carton has a puncture or has a smashed corner. So to find that, I need to find the probability of a puncture plus the probability of a smashed corner minus the probability that it has both, because the probability of both is counting all of these punctures and all of these smashed corners twice. So the probability of a puncture is 0.05. The probability of a smashed corner is 0.08. And the probability of both is 0.004. And when you plug all of that into your calculator, the probability of finding one or the other is 0.126. Next example involves a pie chart, and if these events are on a pie chart, they are mutually exclusive. And when events are mutually exclusive, they can't happen at the same time. So we don't have to worry about subtracting the AND probabilities. These are ages again. You're not going to be under 5 and between 5 and 13. So since they're mutually exclusive, we don't have to worry about any subtraction here. We just have to add. Part A says randomly select someone under 5 years old. That's right here on the chart. So that is 6.6%. And typically we give these probabilities as decimals. So 6.6%, we would answer 0.066. We move the decimal place 2 places to the right to divide that by 100 and make the percent be a decimal. Randomly selecting someone who is not 65 or over. Well, these are the only people who are not 65 or over. So I could go around and add all of these together, but I know the whole pie chart is supposed to be 100%. So let's make this easier on ourselves. It's 100% minus what it's not. So 12.7%. And together that is 87.3%, which we will make a decimal 0.873. Last question, between 18 and 34, well, this is 18 to 24. This is 25 to 34, so we need these two together. So let's add those two together. 12.7% plus 9.9% is 22.6%. And we'll give our answer as a decimal 0.226. Next example. This time we're going from a frequency distribution, and this frequency distribution does not have percentages already calculated for me. It gives me actual raw data numbers. So the first thing I'm going to need to do is add all of those together and get a total. And the total when you add those together is 1,018. And that's just going to make finding the probabilities a little bit easier. Question A says, and actually you didn't have to add, it's given to you in the question that's how many people they asked, so you did not have to add those. If you do add those, you'll get the same answer. Randomly selecting a person from the sample who is not confident, that's this group of people, so that's 112 people, and you simply have to divide 112 by the total. It's just like finding relative frequency back several weeks ago, and this answer is 0.110. This one is an or, so somewhat confident or very confident. That means we need to add those probabilities, or I can just add the raw data numbers and put those over the total. And once I work that out completely, make sure you put this part in parentheses in your calculator. You'll get 0.720 if we're rounding 2-3 decimal places every time. Last example. In a sample of 1,000 people, 120 are left-handed. 2 unrelated people are selected at random from the sample. Find the probability of all of these things. Now, some of these are going to review our AND rule. Remember, the probability of A and B is the probability of A times the probability of B given A. These are not going to be independent events, because once we choose one person, we're not going to put them back into the pool of people to choose them again. So we need to make sure that the second time we choose, we're choosing out of 999 people, and we assume we got whatever we were looking for the first time. So for both people to be left-handed, that means we have 120 out of 1,000, and means multiply. Given this person was left-handed, there are now only 119 left-handed people, and only 999 people total. And when we multiply that, that is 0.014. At least one of the 2 people is left-handed. Well, that means that either both of them are left-handed, or the first one is, or the second one is. Both left-handed we just found, 120 over 1,000, 119 over 999. I'm not going to use this number that I've already found for that because it is an approximated number, and things won't work out quite like we need them to later. So I'm going to just put the actual work back in for the both. Or means add. First person is left-handed, so 120 left-handed people out of 1,000, but that means the second one is not. So if there were 120 left-handed people to begin with, then that means there are 880 right-handed people. So I still have those 880 if this person was left-handed, but there are only 999. Or means add. I want the second person to be left-handed, then I want the first person to come out of the right-handed people. And I have 120 left-handed still there, but only 999 total. And when you carefully enter all of that into your calculator, you will find that there is a 0.226 chance that at least one of the two people is left-handed. Part C says neither person is left-handed. That means the first person is right-handed and the second person is right-handed. So if this person was right-handed, there are only 879 left and only 999 people. And we get 0.774. Part D says two of those events are complementary. Which two are they? We've already talked about the probability of at least one being 1 minus the probability of none, and that works because at least one and none are complementary. So we did part B the long way, but if I had gone ahead to part C and found neither, I could have subtracted 1 minus 0.774 and I get 0.226. So events B and C are complementary, and you can check that out by realizing that 0.226 plus 0.774 adds to 1. Complementary events have probabilities that add to 1. Also, I either have two left-handed people, a left and a right and a left, or two right-handed. And so event B is at least one left-handed. Event C is neither person left-handed. And so it's one or the other, but together, those are all of the possible things that could happen.